Gnanam Paramam Dheyam. Knowledge is supreme.
So, last lecture we have observed some basic facts about the invariants of a subgroup, when invariants of a subset when group G is operating on the bigger set, and we want to apply those observations to our case when a Galois group is operating on the bigger field. So, let us recall what I want to do. So, we have a finite field extension L over K. This is finite Galois extension, and so we have a group attached to that, that is the Galois group, and we have given a normal subgroup H. H is normal subgroup, normal in this. So, remember the notation was like this. This is a normal subgroup, it is a subgroup and it is normal, and then I want to study the fixed field. So, that means fix H L. This is M, this is a subfield of L, and I want to consider this M over K. It clearly contains K, and I want to prove that this extension is Galois. So, to prove M over K is Galois extension. In fact, I want to prove if and only if. So, first I will prove this is Galois, and second I will prove that assuming this Galois, I will prove this subgroup is normal. So, H corresponds to this field extension, this field M. So, we want to prove M over K is Galois if and only if H is normal. So, I am only proving the first part. So, assuming H normal, I want to prove M over K is Galois extension. And what do we want to prove? So, that means we want to prove the order of the Galois group Gal M over K. This order is nothing but the degree of M over K. This is what we want to prove. This is what we are heading to prove, assuming H is normal. All right. So, here is what we have a situation. So, when will H be normal? When H is normal, we know from the observation from group actions, actions tells us that if I want to check that, okay, so I want to check that, so H tilde, this is the kernel of the operation from G. We know that G operates on the fixed field of H. This we have checked that this is a fixed elements of L under the action of H, and we check that this is because H is normal, this fixed is invariant under all action of G, and therefore we have a group homomorphism from G to this, and the kernel of this group homomorphism is because this kernel. So, I want to check that G by H operates faithfully on fix HL. This we know, this is if and only if H equal to H tilde. This is the observation from the group actions we made it, because H is normal. Okay, but if I know that H equal to H tilde, if I know this equality, then I will know that G by H operate faithfully on this fixed field. But I would say, if I want to check this, but H equal to H tilde, because see, I want to prove the two sets are two subgroups. These are both subgroups, and I want to check that they are equal. So I might check as well that their fixed points are same. So this is because fix HL and fix H tilde L. If I check both these are equal, then fundamental theorem of Galois theory will tell you if fixed points are equal, then the subgroups are equal. So this is what I want to check. This implication I want to check. So to prove fix HL is same thing as fix H tilde L. This is what I want to prove. But what do we know? We know that H is always contained in H prime. Therefore, this inclusion, the H is smaller subgroup, therefore fixed field is bigger. So therefore this is clear. This inclusion is clear. To prove the other inclusion, I will take an element here and prove it is here. So let X be fixed point of L under H. Then I want to prove that. So I want to prove that it is here. That means I want to prove that for any sigma tilde. So to prove for every sigma tilde or sigma tilde in H tilde, to prove for every sigma tilde in H tilde, I want to prove what? I want to prove that sigma tilde of X equal to X. Then it will be here. So that is X will belong to fix H tilde L. So this is what I want to prove. But I have given that sigma tilde in H tilde. What does that mean? That means this sigma tilde belongs to the kernel of the map from G to the permutation group on fix HL. This was H tilde was the kernel of this. So, and what is the kernel means? That means sigma tilde should go to sigma tilde here identity. But this is sigma tilde is going to sigma tilde restricted to fixed points of H in L. This is identity on fixed points of L with respect to H. So that means on every element of this, it behaves like identity, but that simply means that sigma tilde, if I evaluate on any element here, and particularly this X is there, therefore this is X. So that proves this equality, and that proves that this equality of the field extensions, and therefore by fundamental theorem of Galois theory, that shows that H equal to H tilde. This is very important. This is where we are using FTGT. So what we proved is their fixed points with respect to H and H tilde are same. Therefore, by fundamental theorem of Galois theory, H equal to H tilde. And we have observed that this fact, the two fixed fields are equal, that is equivalent to saying that H equal to H tilde, and H equal to H tilde is equivalent to saying G by H operate faithfully on the fixed point set. So therefore, what we proved is, therefore H, not H, G by H operates faithfully on this fix H L. Now let us recall what does faithful action means. I remember I want to conclude that this field is Galois over K. This is what I want to conclude. So coming back to understand what does a group operation faithful means. So let us take in general G is a group, and this, suppose this operates faithfully on a set X. That means, so that means by definition the group homomorphism from G to S of X is injective. Faithful means the action of, kernel of the action of the group homomorphism is a trivial. So that means the group homomorphism is injective. So this is injective. So therefore, if I take any element G in G, where does it go? It goes to theta G. Theta G is the multiplication on that set X. This is G going to X going to Gx. This is the bijective map we know, and the G. So when G is not identity in the group, so I will denote identity by 1 without much fuss. So this G, if it is not identity, then this is definitely not identity, because no non-identity element will go to identity element because the kernel is trivial. So if G is not this, then this theta G cannot be identity map of X. So, but then what is theta G? So that means equivalently this map from X to X is not identity. That means if I take this map from G to G, from G to S of X, so that means G going to S of X. So that means what? Now I want to write in terms of the orbit. That means if I take any X and orbit of X, we have a natural map from G to orbit of X, namely any G going to Gx. This map is a bijection because two different G's cannot map to the same. So that means the orbit is a full orbit. That means that the action faithful means, okay, so that means that the cardinality, so that I want to check that this is now equivalent to checking that what happens to the fixed point. So that means we know L over K, this degree we know, this is degree of L over M, which is degree of M over K. But this M over K, I want to shift this to that side. So that means L over K divided by L over M. This is M over K. And this means what? Now the other side, this side I know, this means cardinality of the Galois group of L over K divided by cardinality of Galois group of L over M. This cardinality is same thing as M over K. And now I want to check what? I want to check that this is what we are looking for. This is what we want to check, that this is the cardinality of Galois group of M over K. All that we know is this less equal to this we know, but we want to check equality here. I know this side. This is our H. So this is cardinality of Gal L over K and modulo H, cardinality of H. But this is same thing as cardinality of the G by H. Remember, we are assuming H is normal, therefore this is actually a group. And what do we want to check? This cardinality equal to the cardinality of this. This is what we want to check. But we will check that this action is faithful is equivalent to saying this equality here. This equality. This is because this is if and only if G by H operates faithfully on fix H. This is our M in the notation. Because it operates faithfully, the degree, the dimension will be equal to the cardinality of this group, because this is precisely the orbit. So that follows, therefore we have proved the assertion that, so we have proved, I will just recall, we proved H normal implies M over K Galois. M is the fixed field of L with respect to H. This implication we have proved. Now we want to prove the other way, namely if M over K is a Galois extension, then the corresponding subgroup is normal. This is what we want to prove. And the corresponding subgroup is what? It is, so we have given M over K. So this, what is the correspondence? H corresponds to fix HL, or if I have M here, that corresponds to whom? Gal L over M. They correspond to each other. So this is the correspondence. This is under the Galois correspondence. This is precisely the Galois correspondence. So we have proved that if H is normal, this fixed field is Galois over K. Conversely, I want to prove that if this subfield, intermediary field M, is Galois over K, so I want to prove M over K Galois, then I should prove that this subgroup Gal L over M is normal in the Galois group L over K. This is what I want to prove. All right. So we will prove that. So now we have given, so let us recall what we want to prove. So we have given L over K finite field extension, finite Galois, and we have given intermediary field, and we have also given that M over K is Galois. That is given, that is equivalent to saying the cardinality of the Galois group Gal M over K, this is equal to degree M over K, and degree M over K is same thing as degree L over K divided by degree L over M. This is what we have given. This equality we have given. This is given, therefore we have given this. What more thing we have given? We have given that it is Galois, L over K is Galois. So this means it has a primitive element. We have proved that if we have a Galois extension, then M over K has a primitive element. Has a primitive element. Let us say Y in M. So that means we have given that M equal to Ky, the smallest subfield or smallest K algebra which contain Y. So we have given this equality, that is all we have given. And what do you want to prove? To prove, we want to prove that the corresponding field extension, this group, is normal in gal L over K. This is what we want to prove, because this M corresponds to this subgroup. This is what we want to prove. So, once you understand what is to be proved, things are easy. So, we want to prove this subgroup is normal here. All right. So, that means what? All right. Okay. So, that means that I want to check that what do we want to prove. That's okay. First of all, note the following, that for every sigma in G, I want to check that implies sigma keeps M invariant. This is what I want to check. This I want to check from the assumption that M over K is Galois. Okay. So, to check this, it is enough to check. So, this is what I am checking. It is enough to check that sigma of M is contained in M. Because once I check sigma M is contained in M, then also this is valid for sigma inverse, because we are checking it for every. And then when I apply sigma inverse, then M will be contained in, so it is enough to check this. Or in other words, the degrees of these over K are same. So, once you check this, that is enough, because this is another field whose degree will not change. So, it is enough to check this, and to check this, it is enough to check sigma of y is in M, because sigma of y is in M, because y is a primitive element. So, sigma y will be a primitive element of, so it is enough to check that sigma y belongs to M. All right. So, this is what I want to check. But remember that we have given the formula for the minimal polynomial of y. So, remember that minimal polynomial of y over K is nothing but the product is running over the orbit of y now, gy x minus z. This is a polynomial in Kx. And this is the minimal polynomial of the element y over K, and we have given that M over K is Galois. And remember, this M is this y is a primitive element for this. So, when we have analyzed when the simple extension be Galois, you only have to check the minimal polynomial should split into linear factors over K and into simple linear factors over M. So, this polynomial, we know this splits into simple linear factors in M of x. We know that is because this is Galois. This M over K is Galois. Therefore, this minimal polynomial splits into simple linear factors in this. In particular, all elements in the orbit of y, they are there, because this polynomial has this is the product of mu into the linear factors. All these linear factors should lie in mx, and all of them should be different, but that will mean that all elements in the orbit, they lie in M, but the sigma y is one of the element in the orbit, and that is true for every sigma, because all the orbit elements are here. Therefore, for all sigma in G, all these elements, they lie in M, but that we know that is equivalent to saying sigma of M is contained in M, and that is equivalent to saying that sigma of M equal to M actually. So, that shows that, what do you want to show? That means the whole orbit is contained in Y, but that precisely means the group is normal. Because what is the group then? This is the group gal L over M. I want to show that now this follows that this is normal in this. So how do you prove it is normal in this? It is easy. So it's a subgroup. So we have an injective map here, Lm to Galois L over K, and so this is injective map, and we have given a map. So any sigma, we have checked that any sigma if I take and restrict to M, it maps M inside M. So that means I have given a map from L over K modulo or directly gal L over M, L over M over K, and this map is sigma going to sigma restricted to M. This makes sense. It's a homomorphism from M to M. It's a algebra homomorphism from M to M. That is what we have checked for every sigma in the Galois group of L over K. If I restrict that to M, it goes M inside M, and therefore it is an algebra automorphism of M. So that means it's an element in this Galois group. And when will this be identity? So what is the kernel of this map? Kernel of this map is precisely this subgroup. So this subgroup is therefore a kernel of the restriction map. This is a restriction map. Kernel of gal L over K to gal M over K. This map is any sigma going to sigma restricted to M. That makes sense because this extension is Galois extension. That is what we checked. And the kernel is precisely this one, and that shows that this is, so that proves that gal L over M is normal in Galois group of L over K. So we remember that how do you check some subgroup of group is normal, that is if and only if it is kernel of a group homomorphism, therefore it is normal. So we have proved altogether a statement, the normal subgroups will correspond to the Galois extensions. Galois extension, Galois sub extension will correspond to the normal subgroup. So we have improved the Galois correspondence little bit better because we know which normal subgroups where do they go, or in other words, when the intermediary field extension is a Galois extension. So we will continue this improvement more and more, and that will enhance our understanding of the Galois groups using the group theory. And that is what the main aim of this course is, to understand Galois extensions by using group theory, and conversely understand group theory by using Galois extensions. And then we will concentrate on the polynomials and zeros of the polynomials. So polynomial will give us a Galois extension, and the Galois extension will give us a group, and then we will try to extract information about the zeros of the polynomial by using the group theory. So this is what plan is. We still have many more steps to go, but we will try to accumulate as much as possible. Thank you.